Recursion. Recursion is another approach to looping, where each repetition is dependent upon the result of the next repetition. By solving the next version of a problem, which will be smaller than the current problem, you can solve the current problem. The trick is that at some point, you have to solve a version of the problem that is so small that the problem is trivial. At that point, you stop the repetition and sort of unwind the result back. Recursion is a powerful idiom in code for solving certain kinds of problems. The key part of recursive code is a function that calls itself in its own definition. The add_numbers function shown here calls itself on the 6th line of its own body. This may seem impossible, since it would imply that the function will just keep calling itself over and over again, or that the function would execute before it is finished being defined. You must understand two things. First, successful recursion always requires an if statement or other kind of loop in order to terminate correctly. Second, function definitions happen before function calls, and the body of the function is not executed during the definition. If things still seem murky, keep listening, because we're going to look at recursion quite a few ways before we're done. Recursion is sometimes shown in art, such as this drawing on the left of two hands drawing another picture. In the smaller picture being drawn, there are also two smaller hands drawing an even smaller picture. That smaller picture has two more hands drawing their own picture, and so on and so on. Additionally, we see the painting on the right. An artist draws a painting, and then another artist draws a painting of the original artist holding their painting. In turn, another artist draws a painting of the second artist holding the original artist's painting. The images get smaller and smaller, but eventually terminate at some finite size. At least, as far as we can see. Now let us consider an alternative view, where we are hiring someone to complete a job. We hire Alejandra, who in turn hires two subcontractors Bob and Carol to do the work. Bob in turn hires two subcontractors, Danielle and Edward. Meanwhile, Carol hires two subcontractors of her own, Gregory and Philienne. Eventually, we reach a level where folks actually get the job done. When they finish, they report back their bosses, who in turn report back to Alejandra. By carefully breaking down the work, each individual job is quite small, although we have a lot of employees. The structure we saw before is called a tree, where the structure repeats itself as you go down the tree. Trees are composed of individual nodes, and each node has 0 or more edges coming from below it. These edges connect parent nodes to their child nodes. The nodes at the bottom of the tree without any children of their own are called leaf nodes. The node at the very top is called the root node. There are many ways to represent trees in Python, although we will use a particular structure that works well with the static type system. Parts of this may seem a little strange at first, so pay close attention. First, we define a data class without any fields named tree. That data class is used to create a special constant tree instance named empty, which will represent an empty tree with no children. Then comes the more important and interesting definition for a binary tree. The word binary here refers to how all of our trees will have exactly two children, represented by the left and right fields of the binary tree data class. The third field is the actual data for an individual node in the tree, which we will call value. Finally, we want to draw your particular attention to the parenthetical tree in the header of the binary tree class definition. This extra code is absolutely critical to making the structure work via inheritance. Inheritance actually has nothing to do with recursion. Inheritance is a powerful feature of classes that allow us to reuse fields and functionality between related data classes. This is also useful for describing related types of objects. In this example, since we put media inside parentheses in the headers of both movie and book, we have established an inheritance relationship. That means that all books are media, and all movies are also media. At the same time, books are not movies, and movies are not books. But since these two classes share the name field in common, we have that field in the media class, making it available in both of the two classes indirectly. We could now define functions that consume lists of media and use their name field, which means that we could have a list that contains both books and movies. Even though previously we said that lists could not contain more than one type, those two types are unified by the media type via inheritance. This will be critical in letting us create functions that consume trees, which can be binary trees with 2 children and empty trees with 0 children. Coming back to our definition of a tree, it may help to look at an example. In the code shown here, we end up creating 3 variables to hold tree instances. The first is the empty variable, which we will always create, and holds an empty, boring tree instance with nothing inside. The next variable is a more interesting example named one_tree, which holds an instance of the binary tree data class. Recall that the binary tree class inherits from tree, which means that one_tree is also a tree, just like empty. In order to create an instance of a binary tree, we need a value and 2 other tree instances. We store the value 9 in this tree, which becomes the root value, and then use the empty instance for the left and right children. This represents a binary tree with only one node, which is simultaneously the root and the leaf. The last variable, 3_tree, is even more interesting, since it represents a binary tree with 3 nodes. The root node holds the value 4 and has 2 children. The left child's value is 5 and the right child's value is 7. All of the children's children are empty trees. Now let's return to the employee and subcontractor example from before. This time, we modify our binary tree definition slightly, replacing the value integer field with a name string field. The organization variable holds a binary tree with the name Alejandra, and which has 2 children. The first child has the value Bob and 2 more binary tree in its children, with the values Danielle and Edward. Going back up a level, the second child of Alejandra was Carol, with her 2 children Gregory and Philiane. Although the structure may be a little hard to read, this is all one giant binary tree with 7 nodes. Now, you may be wondering why we use the empty tree as children of the leaf nodes. First, you must remember that we have to pass a tree in for the left and right when making new binary tree instances. That means we must use either a binary tree, which would have 2 of its own children, or the empty tree instance, which has no children. We'll see how this makes our lives easier when we start writing functions that operate on trees. Here is an example recursive function that consumes a tree containing people. In the very first line of the function, we begin by checking if the tree parameter is the empty tree. If we are ever given the empty tree, we return 0, since there are no people in an empty tree. Otherwise, we proceed onward with the body of the function. If we are not in the empty tree, that means we are currently looking at a tree with at least 1 person and possibly 2 children in the left and right. In order to determine the number of people in those 2 branches of the tree, we can reuse the count_people function that we are currently defining. We count the number of people on the left and store the result in a variable, then we do the same for the right. After both sides have been counted, we combine those results with 1, representing the person in this node of the tree, and return the result. Generally, the format of a recursive function always has 4 parts. First, there must be a branch using an if statement at the beginning, to determine if we are dealing with the empty tree, or a binary tree. If the tree is empty, then we are in the base case, and can immediately return whatever basic value makes sense for this case, usually 0 or the empty string. However, if the tree we are given is not empty, then it must be a binary tree, which means we will need to check its fields. We call this the recursive case, and is usually where people tend to get confused. 2 things must happen inside the recursive case: a recursive call with simplification, and combination of the results. The recursive call is when the function we are defining is called right in its own body. The simplification refers to how the arguments to that recursive call should be a simpler version of the original parameter. In our code, that means we use tree.left and tree.right, as opposed to using tree, since those will eventually be the simplest value possible, our empty tree. From a type perspective, this is perfectly valid. Those two fields are both trees, and we know our recursive function takes in a tree. Are they empty trees or binary tree objects? We do not know, and we don't actually even care. The recursive function that we call will handle them either way and return the appropriate result. We just have to trust that it will work out, and continue defining the rest of our function. When the recursive function calls are done, we store their result in two variables, left_side and right_side. We combine these two variables along with the actual value field from the current tree instance. The underscore indicates how this attribute may vary from problem to problem, and the question marks indicate how the combination operator may not always be addition. The final result of the combination is returned, finishing the recursion. Let us look at at least one more example. This longer example finally demonstrates running a recursive function on the entire organization that we defined before. Notice the changes to our recursive function. First, we are now returning a string value in the case of an empty tree, specifically the empty string. Second, in the combination step, we are using the tree.name along with a comma. Since this function gets called on each binary tree, every person ends up having their name followed by a comma. Tracing through this code in a debugger will help you understand the precise and delicate set of calls occurring.